Hi, everybody. Hope you've been having a good morning here at MongoDB.local Austin 2024. How about that keynote presentation? But excited to have you guys all here. And we're going to start off our sessions today with Hemanth Kumar Vemola, our lead platform engineer from Victoria's Secret. Super excited to have him here today with us. And he's going to talk about how they were able to successfully migrate over 2 billion MongoDB documents between CouchDB and MongoDB Atlas with a custom bidirectional replication process, ultimately resulting in 0 downtime, over 3 billion DB transactions, and therefore improving scalability and performance. And so Hemanth is going to be here to talk about how that whole complex migration process went down, some of their key takeaways, challenges, successes, and really excited to hear about how that all went. So without further ado, welcome Hemanth.
Awesome. Check. Awesome. Welcome everyone. I think after that introduction, I'll just really reintroduce the topic. We migrated from CouchDB to MongoDB. And in this process, we had a very interesting migration because these are two separate databases that don't really understand each other while they are NoSQL. So we built a custom bidirectional replicator to facilitate the migration. In this process, we not only were able to migrate the data, but we also unlocked few performance improvements and scalability improvements that we didn't really have with Couch, right? Before we get into the actual migration, a little bit about Victoria's Secret. We are a specialty retailer. We have market-leading brands like Victoria's Secret and Victoria's Secret Pink. We specialize in lingerie, beauty products. We also have a brand called Adore Me that's technology-led and digital-first in nature. All right, so quick introduction about our e-commerce platform. We went from a monolithic platform that was backing a mainframe to a microservice architecture, and that's when we started embracing NoSQL. Back then, we chose CouchDB as our database because that was the only open source CouchDB that could run on Solaris, which was our operating system at that time. While it could run on Solaris, it had a lot of challenges. We were not really able to cluster the databases, so every essential document had to be replicated into multiple standalone databases that had to be indexed, scaled individually, so there's a lot of data duplication all over. Additionally, CouchDB being open source, we didn't really have the support anytime we run into database issues, and there's a lot of cognitive overhead for our developers to understand about how CouchDB internally worked for any performance tuning or anything of that sort. And also during our cloud migration efforts, we tried to lift and shift architecture like everyone does. And while we were able to do that migration faster, it posed a challenge trying to maintain both an Azure footprint and an on-prem footprint with the existing CouchDB architecture. It increased our operational costs and also our operational complexity trying to sync Azure and on-prem. And this is a typical CouchDB topology, right? As I said, we are not able to cluster. Clustering wouldn't work on a Solaris operating system for CouchDB. So if we take any database, for example, let's take a shopping cart database. We had 3 nodes, obviously for redundancy, but all these 3 nodes are standalone nodes. Node 1 wouldn't know the existence of node 2. So we had to set up a custom replication node that would sync the data across these 3 nodes. And while this ensured we had data redundancy, anytime you wanted to query a document, let's say apart from _ID, you wanted to look up a shopping cart based on customer's email address. That was nearly impossible to create and manage indexes on 3 separate standalone databases. So what we ended up doing is create another DB called the keys DB, where we would map the email ID to the _ID of the actual document. And anytime our application would write to these databases, the first write would go to one of these 3 standalone databases through a load balancer, and then we'll make an eventual write into the keys DB. And the replicator node's job was to make sure the data is synced between the 3 nodes, and we would just replicate this architecture for every other database that we have. We had close to 200 databases, and this was a cut, copy, paste architecture for all 200 databases. Now, And to ensure we realized this is not a really good way to operate in terms of being in Azure and other modernization efforts. So that's why we chose MongoDB Atlas. One, it was multi-cloud, so that allowed us to have our workloads in both Azure and GCP, talk to MongoDBs hosted locally in the respective clouds. We were able to automate our deployments and scalability monitoring, and we also had few advanced features like search, charts, and online archive, vector search that didn't really exist in the CouchDB ecosystem. Yeah, so now we know where we were, now we know where we want to be, but how hard is it to migrate our data, right? Now, once we get into migration, obviously our leadership and business will have some expectations, right? And the requirements we got was to beat zero downtime. That is, we cannot take any database offline to migrate it. We had to ensure we are making the necessary schema modifications to ensure we are following MongoDB's best practices. And while we make these schema modifications or migrate the data live, we also had to make sure there are no disruptions to other projects. Like, for example, if you are migrating shopping bag database, there could be other features or improvements happening to that same database, and we couldn't jeopardize that code base while we're doing this migration. So any new features that are being added have to support both Couch and MongoDB. And we want this data replication also to be real time, so that if we migrate to MongoDB and if we had some issues, we can gracefully fall back to Couch and also fall back again to MongoDB once the issue was fixed. And we were doing this on the heels of our holiday. Holiday being important to any retailer and e-commerce platform, we had to ensure that as we migrate, we also establish the corresponding RTO and RPO benchmarks, so that we know if we had an outage in holiday, how to react, and how long would it take for us to restore our services back. Now, these requirements pose the following challenges, right? How are we going to replicate the data between MongoDB and CouchDB? How are we going to make schema modifications and code changes while there are other code changes happening to the exact same code base for other steady state features and bug fixes? And also, how do we build a control plane on top of this replication that would allow us to start, stop, resume the entire replication process, redo the migration if we have any data discrepancies, and how do I control each step of the migration in a surgical fashion? And while doing all of this, how do I account enough time to measure my RTO and RPO benchmarks so that we have a predictable holiday in case we run into issues, right? So we did our data migration planning, and that's essentially, we went back to our basics. We took a crawl, walk, run approach. We categorized all of our 200+ databases into 5 different categories. One is transaction read-write heavy, transaction read-write heavy, non-transactional read-write heavy, non-transactional write heavy, and CX and back office applications. After we categorized this, then we picked one database, and sometimes 2 databases from each of these 5 categories, and migrated them in phase 1. What that allowed us to do is predict all the possible challenges or issues that we could have migrating a database that is of a certain nature. And once we identified all of these things, we would then apply to the upcoming phases. Then we did our phase 2, again, where we went through the entire process and we applied the learnings we have. Once we are confident, phase 4, phase 5, and phase 6, we parallel pathed them, and we concurrently migrated the remaining databases in a matter of 1.5 to 2 months. And once we are stable, we then made operational improvements, scalability improvements, and cost improvements, and then onboarded to the advanced features that we chose MongoDB Atlas for, like online archival or vector search and data federation, et cetera. So some of the in-house solutions that we employed to allow for this migration is we built a custom replicator between MongoDB and Couch, and then we built a wrapper on top of the MongoDB client that will abstract the cognitive complexity for our developers, because as we are trying to go to each and every code base and make code changes, each database workload nature, like if a database is read-write heavy, the MongoDB client would have to be created in a certain way. Versus if a database is being used as a backing store for cache hydration, its MongoDB client needs to be initialized in a different way. Similarly, the way the metrics get instrumented for every command, we abstracted that and built a wrapper library on top of the MongoDB SDK that's open source and available for everyone. Then to ensure all the other projects that are happening for our APIs are happening in parallel, we've created forked versions of our code bases, where essentially we hot swapped the database interface and kept it syncing with the other upstream changes that the application teams were making. And this is just a quick snapshot on how we did our migration, right? Coming from right to left, we had our API consumers, be it mobile apps, desktops, or iPads, anywhere the API call would originate from, it would come to our edge router. And in the edge router, we would control whether our requests either go to shopping cart V1 or shopping cart V2. Shopping cart V1 being the existing application, which was using Couch, V2 being the new modified version, which was leveraging MongoDB Atlas. Now, we would surgically flip traffic between these two versions from 10% to 90-10, 50-50, 80-20, et cetera. And as we gain confidence, we would increase the traffic. And anytime, let's say, V1 gets a request, it would then write it to its CouchDB, which would then get replicated by a replication node into a read-only node. And we would have two replication services written in Golang that were monitoring, that were looking at the change data feed of Couch. And anytime there's a change in Couch, it would shuttle that to Mongo. And anytime there's a change in Mongo, it would then shuttle to Couch. Same thing with V2. It would just write to MongoDB, and our replication service would then take care of shuttling those changes to Couch. Now, in this process, how do we ensure, like, while this allowed us to flip traffic from the MongoDB version of the API to the CouchDB version of the API, how do we ensure we are not in a cyclic loop where we don't re-replicate the same data again and again? So that's essentially where the replication process that we built is cognizant of where the data originated from. It's a very simple flag that we added to our document. For example, let's say a document came to our shopping cart API. It would then go to Couch, picked up by our replication service using change data stream, where it would look for a particular field called updated source. That's something that we manually added to the document. And if that's empty, then it means it was a change that was originated from the application. It was not a change that was originated from a database source. So if yes, then it would then shuttle the change to MongoDB. And it would update a flag called __update sequence to CDB. That essentially, when the change stream on MongoDB triggers again, the replication service would see the updated source as CouchDB, knows not to replicate the change back to CouchDB, and ignores it. Similarly, if any change comes from the MongoDB version of the service, it performs the same logic, and it will ignore that change, ensuring we are avoiding cyclic replication, right? So now we saw how we are able to avoid cyclic replications and how we facilitated API version forking, and we changed traffic from one version to the other. Now, the other requirement is to build a control plane where we have surgical control over the entire replication process, where we can start, stop, resume, increase the batch size, because some databases, you can use a batch size of 10,000. In some databases, you can use a batch size of 100,000 documents at a time to migrate. So we created some config documents inside our MongoDB collections that controlled this replication process, where we had batch size to enable or disable replication. And then on every sync, it would check these parameters to adjust the batch size it was migrating. And then on every sync, we used to capture the metadata on what's the last sequence, the data change sequence that we migrated. Was the initial data migration complete? How many documents were processed? And a bunch of other metadata, which was too long for me to show it here. We were capturing all of these, and we developed a control plane interface where we could surgically control each and every single replication across the board. And we had one for Couch to Mongo, the other for Mongo to Couch. Awesome. And on top of some of these in-house solutions that we used, there are a few MongoDB optimizers as well that allowed us to migrate, make our migration process faster. One is essentially fine-tuning the max index build memory usage megabyte setting in MongoDB. Because once we migrate the data, we then create indexes. Because pre-creating the indexes and then migrating the data made the entire migration process slower. So we first migrated all the documents as is, and then we started to build indexes. But building each index would take a long time. And when you're creating more than one index, it would throttle the database performance because of disk IOPS and various other reasons. So updating it from the default 200 MB to something like 1 GB or 2 GB temporarily, allowed us to build more than one index at a time, and try out multiple indexes as well, because as we are making schema modifications, we had to experiment with the different, especially with compound indexes. We had to make sure the ordering of the compound indexes is correct, the sort order of compound index is correct. So we parallel created multiple indexes and tested the right index that worked for us. Then we increased the op log size from its default for any database that's dealing with a collection over 200 GB. And then during the migration process, we also tried to leverage NVMe clusters where the data read and write would be faster, where we could migrate 1 to 2 terabytes of data within a short span of time. And once the data is migrated and index is built, we would then scale it back down to an M30 or M40, which is what's needed for our steady state workloads. Then to make sure, right, once we have done all this migration, how do we feel confident getting into holiday? Obviously, performance testing and benchmarking every single one of the 200 plus database is not realistic. So we went back again to our 5 different categories, and we picked 1 or 2 databases from each of the categories, and we generated synthetic load against it to test on steady state volumes, 2 times last year's peak on what CouchDB saw. And that kind of gave us confidence on what is the right tier for us to be in for a particular nature of workloads. Once we identified that, we just applied that same scaling logic to all the databases in that specific database workload profile. And for the most part, it remains same. There have been 1 or 2 use cases where it didn't really apply, but those are the cases where we are overscaled, which is a good thing, right? Which we adjusted after holiday time. Then to do RTO and RPO evaluations to make sure during holiday on a Black Friday, if leader election has to happen, or if auto scaling kicks in and scales my cluster, or if Azure's East US2 region is down, what should I expect? And for all of these, you can simulate leader election, you can simulate regional outage, you can simulate cluster scaling up and down in MongoDB Atlas platform. So they have an administration API that we used, and we again picked the 1 database from each of the 5 different compute profiles and executed these tests so that we have an idea on if something like a leader election or a clustered scale up or a regional outage occurs, what do we expect and how do we react? And then since we built a custom wrapper on top of MongoDB client that used the MongoDB events command callback function, we were able to instrument every single command in MongoDB. And that allowed us to capture, while we were doing the above 2 tests for RTO, RPO, and performance benchmarking, we had metrics on both client side and server side. And that essentially allowed us to see how much time we are losing on network and other regions and et cetera. And this is a snapshot of our MongoDB timeline. We started our migration journey towards May. And June 1st is when we completed our first phase. By the time we had completed migrated 1 database from each of the 5 different compute profiles that we categorized into. And then in second phase, we applied the learnings that we had from phase 1. And then in August, we applied, we parallel pathed phase 3 and phase 4 together. And we had to complete our code migration by August so that we have enough time before code freeze, right? We cannot just get our code in a day before code freeze happens for holiday. And code freeze, if you're not familiar, that's something most entities observe during holiday time to ensure we are not putting any new features or anything into production just before holiday and risk the customer experience. And then after we have survived a holiday with MongoDB, we then use the learnings and anything from the holiday we had and applied them and optimized it in place in January. And starting March is when we then allowed our developers and our teams to adopt some of the advanced features like online archive or vector search or data federations, etc. And this is a snapshot of our MongoDB adoption in numbers. In total, we migrated 200 databases, which had 4 terabytes of data in it. We used 89 custom bidirectional replicators. It doesn't mean we duplicated the code. We built a common framework or a library, which abstracts 80% of it. The remaining 10% was schema-based modifications that were different from CouchDB to MongoDB. And that's why we chose to create multiple bidirectional replicators by forking the code base. So that way we can scale something up and down in a surgical fashion. In total, we migrated close to 2.5 billion documents. In CouchDB, we were using a footprint of 1,100 cores because there's a lot of data duplication where each node had to have the entire data. And same thing applied to disk. We went from 120 terabyte disk to 8 terabyte of disk provisioned in Atlas. And so our API saw a performance gain of close to 240%, with all 100% of our data being automatically backed up with scheduled backups in Atlas platform. Right now, we have close to 60 plus autoscale events that happen day in and day out every month. And our cache iteration time, if we have to sync changes from MongoDB to Redis, if Redis cache goes bust or something, the cache iteration time was reduced by 80%. And in this process, we did had some learnings as well. Especially with Atlas, you cannot control the batch size in which it archives the document. So if you're migrating something like order history or purchase history, where you're migrating your transactions from the last 20 years, you don't need all the data from last 20 years to be kept on hot store. But the online archival process itself was taking more than a month. The other option was to scale it to an NVMe tier and do a more aggressive archival policy. But it would have been great if Atlas had a feature where we can control the batch size in which it archives, so that we don't have to choose between waiting longer or paying more to keep things scaled. The other learning was we were not able to do VNet peering due to some infrastructure issues. We had IP address conflict. The other best option, apart from VNet peering, was to use private endpoints in GCP or in Azure. They come with their own challenges. When you are having a multi-region, multi-node Atlas clusters, you have to create private endpoints individually for each zone. And what that would, the implication of that is, if Atlas fails over from one region to the other, your application code now has to connect to a different connection string that's specific for the new region that it has failed over. Which is not really great, right? Because anytime you have regional failovers, you want it to be seamless. You don't want to go in and make code changes or restart your applications to start pointing to a different connection string. So we went with the public global string, which can automatically fail over. It is a downside because it will add latency. You're taking the public internet route and not going through the cloud provider's backbone like in GCP or in Azure. But that essentially allowed us to have a more reliable and controlled failover anytime failovers happen. And the Prometheus integration with MongoDB, while it has the integration, it is an integration at the entire account level. So if you have multiple projects, we distribute our projects per environment. We have a project for test, for non-production, and a project for production. And essentially, we either had to choose our production Prometheus monitoring both prod and non-prod of MongoDB, or the other way around, or make both of them monitor both at the same time, which creates a lot of time series, right? A typical MongoDB Atlas time series has close to 500,000. So you're talking about duplicating 500,000 monitoring metrics, which is not a bad thing to have, but it'll increase some operational overhead and complexity. But yeah, that's our migration journey. I'm happy to take any questions that you guys have. It was really great. We didn't have any sort of negative experience or gotchas per se. Go was supported as a first-class citizen like Java. That was one of our skepticism getting into, because we can see things like JavaScript or .NET or C# being more like first-class citizens, and Golang not for other databases. But at least for MongoDB, the MongoDB Go SDK was great. The API was very similar to what someone would find in Java or the MongoDB command CLI itself. We did have few gotchas when essentially dealing with vector search. For example, LangChain. The Go SDK of LangChain does not support MongoDB's vector store as a first-party integration. We did end up writing our own interface to do vector search and to use MongoDB as the vector store. But apart from that, everything was great. Everything that comes officially with the SDK was great. We had to translate. So if you don't, let me see if it'll allow me to go back. So if you look at our typical CouchDB deployment, anytime our Go applications were writing a document, let's say a shopping bag document, it would write to first the actual database, which would go to one of the 3 databases you see above. Then we would make a follow-up insert into a keys database where we would maintain the relationship between email address and underscore ID. So if there's a use case to look up a shopping cart by email ID and not the underscore ID, we would first hit the keys DB, find its underscore ID, and then make another call to one of these 3 databases to get the actual document. So when the migration was happening, one insert to MongoDB should translate to 2 inserts to Couch, one to the actual database that has the primary document, and then a follow-up insert to the keys database. So that was one. The other one is in some places we were not doing embedded documents where every sub object of a document was its own collection. When we migrated to MongoDB, we started leveraging embedded documents where it made sense for the simplest of use cases. So these are some of the schema modifications and data write modifications that we had our replicators to be aware of. So that's the 90% of the code that we created, and the 10% that's different from each replicator is these small changes, because some collections needed inserting into multiple databases, and some collections didn't require data schema modifications between them. Yeah. Yeah, good. Yeah.
So at that scale, ask out of curiosity, as we're thinking about these things too. At that scale, did you do any sort of relational things as well, like a lookup, kind of MySQL join, do any of that with your data? Or was it just very much NoSQL, pull your documents, display on the screen?
For all e-commerce use cases, it's mostly pull your documents and display it. There are. Yep. Yeah. We gone through that journey when we were going from SQL to NoSQL with CouchDB. But once we were in CouchDB, it was purely the most basic NoSQL use cases. Yeah. So peak business hours, we definitely pre-scaled our clusters. So whatever benchmarks that we established before holiday during our RTO and RPO testing, we just went with those tiers. We could have left Atlas to auto-scale, but that auto-scale takes close to half an hour. It takes half an hour for your either CPU or memory to be triggered. And some of the use cases, especially when you're dealing with cache hydration-based workloads, your CPU is not getting exhausted, your memory is not getting exhausted. What's getting exhausted is your disk IOPS. And there's no auto-scale trigger on exhausting disk IOPS, especially if you're using Azure as your cloud provider. So we definitely pre-scaled, and then we increased our auto-scale tiers, because if we get unexpected traffic, which is a good thing to have, the auto-scale would then come in and help us scale up. But pre-scaling is definitely the recommended way. A couple of clusters did have auto-scaling events during holiday, but at least the most critical clusters that are important for our cache register, all of them did not have any auto-scale. We again leveraged our MongoDB SA's help to come in and analyze all of our clusters way before holiday and help us come up with more safe and conservative disk scaling cluster scaling tiers, so that we can avoid that tense moment of seeing your cluster scale during a Black Friday event. Yeah.
How do you handle concurrency race conditions during back-end cutover?
Yep. So we essentially created a collection to capture all the data replication conflicts. So CouchDB provides an underscore conflict API where anytime, so this is a case where we depended on CouchDB to capture all the replication conflicts that happen between Couch and Mongo. And we used to hit the conflict API, which would then help us resolve that conflict. Which write should win? Should the write from MongoDB win, or should the write from CouchDB win? That's something we leveraged, the CouchDB_conflict API. MongoDB, at least to my knowledge, does not have a conflict resolution API exposed outside of the DB. I know it does within it, within the White Tiger engine, but exposed outside, it was not something that we could leverage. Across all clusters. Correct.